Hello, ladies and gentlemen. I'm Mikhail Zarubin from Technical University Dresden. I'm presenting the paper called Polymorphic Compressed Replication for Columnar Data on Scale-Up Hybrid Memory Systems. To better understand the context and ideas hidden behind, I will go through the paper title step by step, starting from the right. And here we start with scale-up hybrid memory systems, as we use such a hardware as a foundation for our work. Under hybrid memory system, we understand a machine that is equipped with both traditional DRAM and novel non-volatile random access memory that combines features of a storage since it's persistent and features of main memory because it's byte-addressable and has low access latencies. The both memory types are directly accessed by the CPU cores and distinguished only basically on the virtual addressing level. So in such an architecture, we assume that NVRAM replaces the storage, and the data is stored persistently solely in NVRAM. As well as we assume that such machines follow the scale-up paradigm or non-uniform memory access architectures. So they are compound of several NUMA sockets which are symmetric, and each of them is equipped with both DRAM and NVRAM. They are connected using high-speed interconnects, so local memory accesses are still faster than remote. Such architectures have already made a huge impact on the database systems, because finally we can have a real true in-memory databases because there is no slow secondary storage which is block-based, and all the data processing is done in byte-addressable way. That offers a huge performance increase as well as opportunities for instant access and recovery. Nevertheless, there is a challenge. Since the data is stored persistently solely in NVRAM, there is a need for its protection because there are a number of possible NVRAM failure scenarios. So with regard to the data processing model, we rely on columnar data organization, which is kind of a state-of-the-art in analytical processing, for example, in big data. And under column, we understand a sequence of values mapped to integers. For modern processors, these are 64-bit integers. And query is a sequence of operators that is executed on such columns. So now we covered the second line in the paper title, and I will proceed with the first line. So here we start with the word replication. So why we actually target the replication as a data protection technique? So the main reason that the recent research and industry has already accepted it as the most reasonable protection technique for hybrid memory systems, as it has a number of advantages features. First of all, it is able to protect primary data against most or even all possible NVRAM failure scenarios. It could be implemented in software to achieve desired level of flexibility, and to achieve the best performance, we can go for physical level data transfers or memory region implementation. And if we require strong consistency property, we select the synchronous approach. So the state of the art is represented by the Intel Persistent Memory Development Kit Full Replication Library that follows a synchronous master-slave model. So I will briefly illustrate it on that slide. So here we allocate one master and two replicas, one local replica and one remote replica. If the modification comes, it's first is propagated to master and then sequentially to every involved replica. The whole process is successful if all replicas are processed. Okay, so there are a number of drawbacks in this approach which we actually target to mitigate, and the first one that we identify is the NUMA awareness. So as we see in the existing approach, we can place a replica on the remote socket. However, this is done statically and we cannot change this at online and at per data structure level. So the existing approach is not really fully NUMA aware. And another drawback here is that only masters are readable in the existing scheme and replicas are only used for recovery purposes. The second drawback is that the state-of-the-art approach deals only with NVRAM replication. We may want to place some replicas in DRAM for query processing needs. And there is a general drawback of most replication schemes, the storage overhead. So having one replica implies to the reservation of 100% of additional storage space. So in our paper, we propose a number of ideas to to mitigate these drawbacks, as well as to leverage replication for query processing needs. And the first idea is concerned with the word replication in the paper title. So here we suggest to enable per data structure NUMA allocation policy as well as replication policy that makes the whole approach more flexible. We can avoid unnecessary replication of secondary data. And another idea here is to enable not only masters to be readable, but also replicas. That can potentially provide a huge speed ups because we can efficiently utilize the hardware resources. So for dual socket machine, we can basically double the performance. The second idea that we propose is to enable the hybrid memory replica placement. So basically, that means that we now provide a unified scheme for NVRAM and DRAM replication. There is no principal obstacle for doing that because DRAM and NVRAM are only distinguished at virtual addressing level. So we can place some replicas in DRAM to achieve better performance because DRAM has much higher bandwidth and low latencies compared to DRAM. As well, it also would free some persistent capacity. Okay, so finally we reached the word compressed in the paper title. And here we propose to use the compressed formats of replicas and possibly masters. So that idea mainly targeted the mitigation of the storage overhead problem because as it was shown recently, data in NVRAM can be efficiently compressed similarly to DRAM using lightweight compression algorithms. And that also would contribute to the wear-out minimization since we are doing less writes to NVRAM. The runtime overhead also could be reduced because we can transfer then more logical data within same physical limits. Therefore, yeah, the effective bandwidth is increased. And query execution can also benefit from that because it can deploy the compressed formats. For example, scans would need to process less amounts of data. Okay, so, and the final idea, which we call polymorphic compressed replication, actually suggests to use various compressed formats for different replicas of the same column. And here, the advantage is that we can then average the storage overhead since there is no single best compression algorithm and the effectiveness is depends on the data characteristics and as well on the access pattern. So having a variety of them, we can mitigate possible drawbacks of just single one, as well as from the query execution point of view, we can adaptively select the best suitable format of the column adapt like an online way. So having these four ideas, we can say that now we are able to efficiently deal with identified replication drawbacks, as well as leverage replicas for the query processing needs. And to verify that our concept actually works, we developed an abstract user space library. So we call this library PCR, and its goal to hide complexity of our ideas behind Simplify API. It was integrated with our in-house query processing engine called MorphStore, and we've shown that user application mostly need to change only memory management calls. So here we have an abstract handler instead of row pointer, which is used for allocation. So we have allocate call similar to malloc to actually allocate all necessary memory buffers. Then to get the actual data for reading purposes, we have a get buffer call that will return the best suitable replica of a column. And then to modify data, we use the append call similarly to big data and data warehousing systems. Deletion done in a normal way. So we use this library to evaluate that our concepts are actually useful. And we've shown that every standalone technique could be beneficial like as a standalone, and we can also combine them arbitrarily and deliver up to 5 times speed up. However, the actual improvement would depend on the access pattern, number of threads, data characteristics, and system workload. For more experimental results, I invite you to read the paper. And now I'm done with my presentation, and thank you very much for your attention.
We have time for a quick question. I see that we have one from Danny Harnick. He says, excellent talk, and asks if you can elaborate a little bit about the compression techniques and how you choose the right compression method for various data.
Yeah, okay, so in our work we focused on the null suppression lightweight integer compression algorithms. So the particular cases were static binary packing and dynamic binary packing. We used these two for our experimental evaluation. Yeah, so actually they deliver can deliver a good compression rate. However, that depends on the data characteristics. And here we do not pretend that we actually adapt to the data characteristics because, yeah, that's a little bit out of the scope. Instead, we provide various compressed formats so that if one data compression algorithm doesn't compress good, so the other one could mitigate possibly the problems of the first one. And therefore we achieve the average storage overhead reduction, as well as query processing can select adaptively the best suitable format for query processing on compressed intermediates. So hope that answers the question.
I think it does. Thank you. I have another question while others are typing in their own questions. You mentioned that of the 4 techniques, their combination and each and every one of them provide performance improvements. Can you name, or is it something that is variable, one of them that is more dominant than the others?
Yeah, so I would say that there are a variety of scenarios and a variety of use cases. So I cannot name the single best one because there are always situations. For example, we can place all the data in DRAM that will hurt our resilience because we are losing the persistent data, but DRAM has a higher performance, so we can run all our sockets only using DRAM memories, and then it's will at least, you know, DRAM has a much higher performance than NVRAM. And again, that could be selected using on some user knowledge, or then a future direction could be do it adaptively when we write the replicas actually. But yeah, so.
Okay. I think we have again time for one last question by Michael Factor. He asked, what is the performance overhead of trying different compression approaches? And do you have a good view of how to manage the CPU memory network trade-offs here in the context of compression?
Okay, so yeah, in fact, having a different compression schemes actually leads to a little bit higher overheads comparing to have single one, because then we can just compress once and copy it to all involved replicas. But instead, we need to execute a specific compression algorithm. Nevertheless, in our evaluation, we've seen that it's more than acceptable. So in some cases, there is no even difference because the lightweight compression can achieve a very good performance. So from that point of view, we didn't see major bottlenecks. And yeah, so from the trade-off point of view, have a compressed data written to replicas, better utilize the available NVRAM bandwidth, for example, because we need to actually propagate less data because it's compressed now. And therefore, we can actually save the effective bandwidth here. So yeah, I think that would be the short answer.
Great, thank you very much.